This is our second titration curve video. So in the last video, we were talking about what's occurring during the titration and how we can identify the equivalence points. So the sudden drop in pH, halfway through that sudden drop is the equivalence point. That this was a polyprotic curve because we had more than one equivalence point. And that the equivalence point will allow you to select the indicator. So the indicator needs to line up so it's changing around the equivalence point, or like I like to think of it as sandwiching the equivalence point. Well, in this video, we want to talk a little bit about buffers and buffer solutions. So buffers resist change to pH, and they are made out of a weak acid and a conjugate weak base. So the reason for having a buffer is to resist change in pH. There are lots of biological reasons for that. We don't want the pH to change in our bodies dramatically, or it could kill us. In a lot of chemical systems, keeping the consistent pH will protect our equipment or encourage the right kind of reactions to occur. So buffers are really important. Buffers are made out of a weak acid and a conjugate weak base. So for instance, here you've got phosphate ions that's a negative charge. Phosphate ions are starting. If you had hydrogen phosphate ions with phosphate ions, that would be a buffer solution. If I had hydrogen phosphate ions and dihydrogen phosphate ions, that would be a buffer solution. If I had dihydrogen phosphate ions and phosphoric acid, that would be a buffer solution, because each of these has a weak acid and a conjugate weak base. But in this curve, when we're looking for the buffer regions are always going to be flat. So the flat regions are possible buffer regions. And so we've got three possible buffer regions here. But in this case, we can see that you have a strong acid. A buffer can never have a strong acid or a strong base as the major entity. So up here, we had our polyprotic base and its conjugate acid. Here we had a weak acid or base and its conjugate weak acid. But down here, what we've got is a bunch of hydroniums. So the pH change here is because of the hydrochloric acid. So this is not actually a buffer region. This is a region, and this is a buffer region, but this is not. So we're going to take a look at another curve and try to make sense out of that. Now in this, it's got a polyprotic base, so it's got a sulfite ion, and they're adding hydrochloric acid to it. And as they do that, they're going to make hydrogen sulfite ion. We have one identifiable equivalence point here. So if I was picking a buffer, I want it to sandwich that. Down here, the entity that we're going to mostly have are hydroniums. So at the end here, we're not going to actually have a buffer region, but this is a buffer region because this has got a base and its conjugate weak acid. So this is a buffer region, this is not. Up here, you're going to often see these kind of like little limp tails or something like that. What that is that's actually the hydroxides from when the sulfite ion reacts with the water to make hydroxide ions and hydrogen sulfite. So that happens at the beginning, and those hydroxides react very quickly with hydrochloric acid. So we get this like kind of little limp tail. But once those are used up, then all we have left are the sulfites to react with the hydrochloric acid. So you get the sulfite and the hydroniums from the hydrochloric acid to make hydrogen sulfite and waters. And so that's what the buffer mixture should be here. Down at the bottom, all of the base has been used up. And so really at this point, once they get down here, they're really just adding acid to an acidic solution. So it just stays flat because it's just more acidic. Now this graph shows a few things that are a bit hard to see. If you have a strong acid and a strong base, and they're monoprotic, they will have a nice, smooth, sharp titration curve, and we would expect that the equivalence point should be at pH of 7. If instead I had a weak acid and I had a strong base added to it, it's going to go like this, and you would expect its equivalence point to be greater than 7. Because it's a weak acid, it's not going to be super great at reacting with a strong base, so its equivalence point is greater. If instead I had a strong acid and a weak base, its equivalence point is going to be less than 7. And so we can sort of anticipate generally what kind of a pH we might expect when we're selecting our indicator. But the curve will tell us, because if I know that the pH at the equivalence point is 4, then I select that using my data booklet to find something that's going to sandwich 4, like methyl orange perhaps. Maybe bromocresol green, depending. Okay. This is our last curve that we'll look at, and in this one we have a phosphate and hydrochloric acid. Oh, never mind, we've already seen that.